The topic for this video is covalent bonding. The essential questions are: what is a covalent bond? What properties do covalent compounds share? And what is the difference between polar and nonpolar compounds? So a covalent bond is when you have a shared pair of electrons between nonmetal atoms. Okay, for instance, two fluorine atoms. They have 7 valence electrons, okay, and they want to have 8. So what they do is they share a pair, and that makes a covalent bond. And now they are both sharing 8 valence electrons. And we call that F2. Okay, same thing happens with hydrogen. Because hydrogen is only in the first shell, they only want 2 valence electrons. So they each have 1 to bring to the table. And so by sharing theirs, they both can share 2. And that makes a covalent bond. And that's called H2. So those are examples of some diatomic elements, which means that they're elements in nature. They always find a way to bond to each other if they're not bonding to a different type of element. So they never exist just by themselves. So you'll never find one hydrogen. It's always going to be H2. Same is true with oxygen. It's never by itself. It's going to be O2, fluorine, bromine, iodine, nitrogen, and chlorine. These all exist as a pair with itself if it's not bonded to something else, okay? But it just won't be an N, or it just won't be a Br. It's going to be bonded if it's by itself, okay? And so you're going to need to remember these, because when we write chemical equations and do other things, and it says you're adding oxygen, you're going to write O2 instead of just O. Or if it says you're writing hydrogen, you'll write H2 instead of just H. So the way to remember this, I just remember Hofbrinkel, kind of like it's somebody's name or something, Hofbrinkel, and that helps me remember. These are all going to follow the octet rule except for hydrogen and helium, which means that the atoms share electrons in order to have 8 valence electrons, but again for hydrogen it's going to be 2, and helium already has 2, so they're not going to participate in bonding. So let's talk about the degree of sharing between nonpolar covalent, polar covalent, and ionic. So in nonpolar covalent, the electrons are shared equally. The atoms have very close to the same electronegativity, which means how much they want to pull on electrons. And so they pull on them the same, and so they're even. Okay, like 2 H's are obviously the same type of atom, so they have the exact same electronegativity. With polar covalent, the electrons are still shared, but now they're shared unequally, and there's a medium electronegativity difference. Okay, this is true with hydrogen and chlorine. That is a polar covalent bond. However, chlorine can pull harder than hydrogen, kind of in their tug of war with electrons. And so chlorine holds the electrons closer to it than the hydrogen does. And that means it's partially negative, which is that little sign there. A little squiggle is a lowercase delta for Greek letters, and you put a delta and a negative, it means it's partially negative. You can do the same thing with positive. The hydrogen doesn't have that electron as close to it, so that makes it partially positive. Then you have ionic, which we've already talked about, and one atom takes an electron from another, and there's a large electronegativity difference because one doesn't hold them hardly at all. So for instance, the difference between sodium and chlorine, okay, sodium has its electron, and chlorine is able to steal it completely, and then they're just attracted to each other because of their positive and negative charges. Okay, so here's an electronegativity chart, and to give you kind of an idea, we're going to say that delta electronegativity, which is the change in electronegativity, we'll get that just by subtracting 2 elements. So if the change or the difference is 0 to 0.4, that's going to be a nonpolar covalent bond. If it's between 0.5 and 1.9 when you subtract the 2 elements involved, that's going to be a polar covalent bond. They're still sharing, but they're sharing unequally. If it is 2 or bigger, that means that they are not sharing anymore. They're transferring electrons, so that's an ionic bond. Okay, but there is a little bit of gray area here, so this is just a rough guideline. The bigger the electronegativity difference, the more polar or the more ionic character it has. So we're going to practice using electronegativities to rank these bonds from the least polar to the most polar. So if I have hydrogen and fluorine, hydrogen is 2.1 and fluorine is 4. So I'm going to subtract the 2 and I get 1.9. Okay. Then carbon and sulfur actually have the same. 2.5 minus 2.5 is 0. Carbon is 2.5 and hydrogen is 2.1. So we subtract, we get 0.4. And then calcium and chlorine. Chlorine is 3, has an electronegativity of 3, and calcium has 1. Okay, and we subtract and we get 2. And it doesn't matter how many of each we have like it does with the formula. We're just going to take the two elements that are being combined, however many of each type, and subtract. Okay, so now it wants us to rank them from least polar to most polar. So the least polar is going to be closest to nonpolar, which is 0. So this is going to be our least polar. Okay, then we're going to just work our way up from there because the difference is 0. The next highest is C and H, which is a difference of 0.4. Then we have H and F with a difference of 1.9, and then the most polar is going to be Ca to Cl. Okay, we're going to do the same thing down here. You can go back and look at the electronegativities between K and I. I is 2.5 and K is 0.8. We subtract, we get 1.7. Sulfur and oxygen. Oxygen is 3.5, sulfur is 2.5, so we subtract and we get 1. Barium and fluorine. Fluorine is 4 and barium is 0.9, so we subtract, we get 3.1. And iodine and iodine, well, we know those are going to be the same, so we don't even necessarily have to look that up because it is 2 of the same, so if we subtract the same numbers, it's 0, but iodine is 2.5. So now this one's least ionic to most, so again, we're looking for the smallest difference to the biggest difference. So we'll start with 0 as our smallest difference, and we'll work our way up. SO is next with a difference of 1. Ki was next with a difference of 1.7, and finally BAF was a difference of 3.1. Okay, another type of covalent bond is a network covalent bond, and this is a giant sharing arrangement. It's a really strong bond. A diamond has this bond. A diamond is pure carbon. Quartz also has this bond, which is silicon dioxide. And so these are allotropes of carbon. So we have diamond, which is formed with this network covalent bond, which is kind of in a grid. You have graphite, which is like what's in your pencil. Okay, and it's formed a little bit differently in layers. And then you have what's called a buckyball, which is carbon forming circles. So these are all different types of how carbon can bond, and that's called allotropes. Okay, let's talk about the properties due to types of bonds. An ionic bond, okay, so this is partially a review. An ionic should be a metal with a nonmetal. Polar covalent and nonpolar covalent are 2 nonmetals together, or more than 2. Metallic are with metals, and a network covalent is going to be with nonmetals. Okay, let's look at the electronegativity difference. It's going to be very large with ionic. It's going to be medium with polar covalent. It's going to be very small with nonpolar covalent. It's not important with metallic. And it's not important with network covalent. How the bond is formed with ionic, you transfer electrons. With polar covalent, you unequally share the electrons, and with nonpolar covalent, you equally share electrons. Metallic had the sea of electrons, and network covalent had the sharing of electrons in a lattice. Okay, let's look at solubility in water. With ionic, it is. Polar, it is. Nonpolar, it's not. These are like oils. Okay. Metallic is not. Okay, you're thinking about metals. They don't dissolve in water. And network lattice, like a diamond, is not. It does not dissolve in water either. Okay, do they conduct? Ionic, no if they're solid, but yes if they become melted, which means they're a liquid, or if they're dissolved in water. Polar is going to be poor. Nonpolar, it's not going to conduct. Metallic, yes it will. Those are metals, they like to conduct. And network, no for the most part. Ionic exists as a crystal lattice, which means an orderly structure. Polar and nonpolar, all covalent, is just separate molecules. Metallic and network are also crystal lattices. Melting points for ionics is high. Polar and nonpolar is comparatively low. Metallic is high for the most part. and network is very high, like it's very hard to melt a diamond. Other traits, ionic tend to be brittle. For metallic, they're malleable, which means we can hammer them into a sheet. And network, covalent, are very hard. For an example compound, ionic, we have our classic example of sodium chloride, which is table salt. Polar is ammonia, NH3, or even water, H2O. Nonpolar is like wax, hydrocarbons, oils, things that typically do not dissolve in water. A metallic bond would be like aluminum has. And our example for a network covalent is a diamond.